Hello everybody. Today we'll see the gravitation chapter. I have divided this entire gravitation chapter, which is there for the 11th class 11th as well as the NCRT book and the NEET and JEE syllabus, into three parts. So this is part 1. The part 1 indexes what are the points which I will be covering in part 1 is the introduction of gravitation, then the Kepler's laws of planetary motion, universal law of gravitation, then measurement of G, that is gravitational constant with the help of Cavendish balance. Next point is acceleration due to gravity, and then we'll see the variation in this G, acceleration due to gravity due to the alteration of altitude, depth and latitude. This is derivations and formulas, so we'll find. Then we'll also see the shape of Earth, the point which we'll discuss in detail, then gravitational potential energy and the gravitational potential. The remaining part we'll see in the escape velocity, and then so there are so many other points. There are many, weightlessness, and so we'll see in the part 2. But in part 1 we'll see these points, right? We'll focus on this. So let us start with the introduction. There are a few points which we need to understand. Naturally, every massive object in the universe experiences a gravitational force of mutual attraction by virtue of their masses, and this force is of infinite range. It is applicable for a large range. Now, what exactly this means is every object, every massive object attracts any other massive object due to the gravitational force, and this is a natural phenomenon. Every object, right, massive object. Now the next point is all bodies are attracted towards the earth with constant acceleration, and this fact was recognized by Italian physicist Galileo. Aryabhatta, Tycho Brahe and Johannes Kepler studied these planetary motions in detail, and they gave their own outcomes. So we'll see these outcomes also. Especially Newton explained gravitation is the phenomenon responsible for keeping planets in their orbits around the sun. Why the planets are moving around the sun is basically this force of gravitation is there. Fine. So we'll see now. To understand the Kepler's laws as well as the gravitation, the concept of gravitation and Newton's laws, we must understand what exactly this ellipse is. Reason being, this ellipse concept and the geometrical figure ellipse is completely associated with this gravitation chapter. So to understand ellipse, let us first understand what exactly we know. We know circle, right? And we know what are different peculiar characteristics or points associated with circle. We know that circle is the shape and it has a center. We know it has a radius, and what exactly radius is. We know what is diameter and where exactly it is connected to points, and then what is the relation between radius and diameter, as well as we know the tangent. We know the area of circle, the formula for that, and we know the circumference. So these are the points which we know about circle. Now let's see this is a geometrical figure. Now see another geometrical figure which is analogous to circle but of this shape, the egg shape, right? Now what are the points which are there and which we need to understand the further points. So again, ellipse has a center, but ellipse has a axis connecting to farthest or the longest points, and that is called as major axis, and half of it is called as semi-major axis. The line joining center and the farthest point, right? One of the farthest point is semi-major axis. Similarly, the line joining two shortest point on the ellipse is called as it's minor axis, and the half of it is called as semi-minor axis. Now just imagine this the ellipse, the internal part, the inner part of the ellipse, inner part of the ellipse is coated with some reflective material. Just imagine, and we allow light to fall on the surface. Now if we do this, what will happen? The light get reflected back and focus at a particular point, and this point is called as a focus. This is a geometrical parameter of ellipse. So a line, this is not there with circle, right? So this is called as focus. Similarly, if this is there on the right hand side, left hand side also we have a same shape of ellipse, so we have another focus on left hand side also. So an ellipse has two focus, that is called as foci. two foci. So with this, what exactly, so we know what exactly mean by semi major axis, semi minor axis. We have understood what exactly mean by focus. So these are the points which we will use it for the further understanding of Kepler's laws and this. So let's move to the further point quickly. So Kepler's law of planetary motion. So what this Kepler scientist who has given the laws of planetary motion, Kepler's laws of planetary motion describes the orbits of the planets around the sun, the planetary motion, how exactly the planets revolve around the sun. He published first two laws in 1609, so 400 years back, more than that, and the third law in 1619. So we'll see. So it means that there are three laws, Kepler's laws. We have already have a small feeling of it. Like, let's see, the first is law of orbit. The first law, Kepler's first law states, is the law of orbit, and the statement is all planets move in an elliptical orbit around the sun, with the sun at one of the foci of the ellipse. So planets are moving in an elliptical orbit and sun is at one of the foci. So let us understand with some graphics, right? This is ellipse, alright, and then semi major axis and semi minor axis. Now this is any planet or earth, take an example, and then sun is situated at one of the foci. This is what is law of orbit, and earth revolves around the sun in an elliptical orbit, and the period of this earth is, you can say, it is 365 days. Okay, so this is law of orbit. Now we'll see law of areas, the second law, Kepler's second law, popularly known as law of orbit. The line that joins a planet and the sun sweeps equal areas in equal interval of time. Now let us understand it. Now we will understand it more with the help of some animation, right? Now this is an ellipse. It has semi major and semi minor axis. So sun is situated at one of the foci. Now a planet is positioned at point A. Imagine any planet is positioned at point A, and the line joining between the sun and the planet is, this is what is the blue line. Now that is what is important for us, the line joining. Now just imagine that the planet moves from position A to position B in one day. Planet moves from position A to position B in one day. It's an imagination. We know that planets are moving, like for example earth is moving around the sun. Period of the revolution is 365 days. Out of that, the planet has moved from point A to point B in one day, and the area covered by this line is A1. This is what is the area covered by the planet from when it is moving from point to A to B. Now consider another situation when the planet is at point C at position on the ellipse, and in exactly one day it moves to point D, and if the area swept from C to D in one day is, for example, A2. And another situation we can consider, the planet is on some other day is at position E, and it moves from E to F in one day, and the area swept is A3. Now what this law of area says, that this A1 is equal to A2 is equal to A3. So what does it mean? That area swept is equal in equal interval of time. So this is a formula, but it has a different meaning. Physical interpretation is different. What does it mean? Just concentrate. It is very important, right? Now, what does it mean when the planet is when planet is near to sun? When planet is moving near to sun, it moves faster. It covers more of the path length will be more. Right? When the planet is away from the sun, it moves slowly. So our earth, when it is near to sun, when it is moving from point C to D, it moves faster, and when it is moving from A to B, it moves slower. So this is what we should understand it very, very clearly. So it means that when this is a position number 1, so this is 1, so this speed of the planet will be highest from point C to D. It will be somewhat lower from point to E to moving from point E to F, but it will be the slowest at this position from A to B. It's a derivation of we'll see this derivation to prove the laws of areas, and it's an important derivation. So the law of areas can be understood as an outcome of conservation of angular momentum. Now we know what is momentum. Momentum is mass into velocity. Any mass into velocity is called as momentum, but there are two types of momentum. One is angular momentum and linear momentum. When something is moving linearly, something is, we'll see this in detail, but when something is moving linearly, it is called as linear momentum, and if something is moving in circular motion, circular motion, it is called as angular momentum. So two type of momentum: linear momentum, angular momentum. Linear, when things are moving linear in a linear direction in a straight line. On the other hand, angular momentum, when the body or an object is moving in a circular or an angular motion, right? So this is what the area swept by the planet of a mass m in given is equal interval is given by area. Area is given by, now its area is a vector, right? It's a vector because it's changing with time. So area is a vector, is a half base into height. Now this, we know this area is half base into height is basically it's a basic formula of a right angle triangle. So we have to see that the area swept is basically a right angle triangle. So what is it? Now we must understand what is this, right? So what is this delta t? Delta t means a very small time. Like for example, we have taken in that figure, the previous figure which we have drawn is basically the area for 1 day, right? Time is for 1 day. Now let us consider for only 10 seconds. So what will happen? This area, this distance will be very small. This distance will be very small, and the distance is very small, hence the area is also very small. So what delta a and delta t means? Delta a means delta a, when delta t is very small time, means area is also very small. So this is very small distance, this distance will be very small, and when the distance is very small, it will be as good as a straight line and not a curve. It will be as good as a straight line, and when this is as good as a straight line, and this radius and tangent makes an 90-degree angle here. When it makes a 90-degree angle, it will be a right angle triangle. So indirect, what exactly the approximation, a small approximation of delta t gives me an opportunity. It's a very easy for me to understand calculate the formula of area. It's base into height. Now where exactly from? Now this is r into, so one side is r and other side is v into delta t. So what is one side? We know this one side is r, the radius of the you can say it's an ellipse, okay, no problem. So it's a radius of it. Now what is the second side is v delta t. Now what is this v delta t? Now, velocity into time. What is velocity into time? Velocity into time is, you can see from here, velocity into time is basically a displacement. So it is a distance. It is a distance. So this v into time, this distance is written in terms of velocity into time. Remember forever. There will be so many instances and so many derivations and so many formulae will come and numericals will come where you have to write a distance in terms of velocity into time. Many times you will be using it. So don't forget this. This is an important formula. Distance we are writing in terms of velocity and time. So this is the formula for radius. This is the formula for area swept by small areas. This delta stands for small area. This is for small time. So this is the area. So let us move further. So if I take delta t this side, so it will be delta a upon delta t is equal to half r into v. So this into, now as these are vector quantities, this into we call it as a cross product. We have seen that in the first chapter, right? So this is cross product, so r cross v. So this multiplication of vector is cross product. So delta a upon delta t is equal to half cross r cross v. Now this, let us understand linear momentum. Now linear momentum, as I told, linear momentum, the symbol is p and it is formula is m into v, mass into velocity, and linear momentum is a vector quantity as it is a multiplication of scalar, and velocity is also a vector quantity. So linear momentum is a vector quantity, first point, and second point the formula is p is equal to mass into velocity, right? So if you calculate v from this, that will be p upon m, right? Just see it. I have just calculated v because I want to substitute this v into the previous equation, this equation, right? The previous equation was delta a upon delta is equal to half r cross v. So if I substitute this v, here, what will happen? Just check this v here, what will happen? Delta a upon delta t, so half will remain same, r is remain same, and p in place of v we have substituted p upon m. Now here these are two vectors, but m is not a vector, we know that mass is not a vector, so I can take it out, right? So angular momentum L, this is called as angular momentum L in the rotational equivalent linear momentum is given by, this is the formula for linear momentum. Now let us see the angular momentum. What is angular momentum? Angular momentum is momentum due to rotational motion, right? So the formula for that is L is equal to r cross p. So relation between angular momentum and linear momentum, it's an important formula which gives me the relation between angular momentum and linear momentum. So L is equal to r cross p. So if I substitute this equation number 5 in equation number 4, the delta a upon delta t will be L this r cross p. So in case of r cross p, what I am doing, I am substituting r cross p is equal to L. So is equal to half will be same. So delta I upon delta is equal to L upon 2m. L is constant because angular momentum is constant. 2m, so everything is constant. So rate of change of area is constant. That is the proof of the second law of areas by Kepler's second law. Rate of change of area is constant, means the area swept by that line joining is constant. So that's what rate of change of area swept is constant. This proves the laws of areas. I think it's very clear, right? So the second, this we have seen the second law, laws of areas. Let's move to quickly to this third point, that is law of periods. The third Kepler's law is law of periods. The square of the time period of revolution of a planet around the sun, that is t, is proportional to the cube of the semi-major axis, that is r, of the ellipse traced by the planet. Now this is the statement. Let us understand the statement with the help of figure. It makes it very easy. Now let us again, ellipse, semi-major axis, semi-minor axis. Now this earth is revolving around the sun in an elliptical orbit. Sun is situated at one of the foci. Now if it is revolving around the sun and t is the time period, to complete one revolution, and r is the distance of semi-major axis. So what is the formula says? What is the statement says? T square is equal to r cube. T square, square of the time period. Now here it will make very easy. See, T square means what? Square of time period of revolution. T is proportional to right? Is proportional to cube of the semi-major axis traced by the planet. So this is the law of period. This is the third law, Kepler's third law. So I hope you have understood the first law, law of orbit, law of areas, and law of periods. These are the three laws of Kepler's law. And even the second proof is also very important, where we have proved the area swept is constant. Fine. So it's an interesting table where tells me, it's very interesting. See it now. It's what this table tells me, the period of planets of our solar system, right? All the planets which are there in a solar system are listed, and their period is also listed. Just see column number 1 and then just see these two columns. First we'll see these two and then we'll move further, right? These are the two columns. Now planet Mercury, let's go to the Earth. Now Earth completes its one revolution in 1 year, right? Earth completes its one revolution in 1 year. Similarly, other planets, see, the Mercury completes in 0.25 years, matlab those many days only, right? So you can calculate how much. So 365 into 0.24, this is the time period of the Mercury, and then Venus and this. Now look at Pluto. Pluto requires 248 years. 248 years to complete one revolution around the sun. It's not joke. 248 years to complete the one revolution around the earth. So you can see it, and then in other these points also they have given explain the semi-major axis. What is the semi-major axis for that particular planet, and the ratio of t square upon r cube also they have given. So semi-major, you can see the semi-major axis is increasing. As semi-major axis is increasing, the period also increasing, right? So because distance we are getting away. This is an important point of this planetary motion, right? Is calculated just sitting in the bedroom or just sitting in the office. So nice of the Kepler and gravitation. So they have worked so nicely. Just with using the mathematical formula and concept, we could be able to find out the different values. Fine. So this is another example. So let's move. The further point is, next point is universal law of gravitation. Now what is universal law of gravitation? There are few points which we need to understand first. Now Galileo pointed out that heavy and light objects, when released from the same height, fall toward the earth at the same speed and same acceleration. Galileo, what is, when two objects are released from same height, then they will fall with same speed and same acceleration. The speed and acceleration will be same. Now Newton stated the universal law of gravitation. Moon completes one revolution around the earth in 27.3 days. right? The revolution of that is the period of moon around the earth. The distance from the earth to moon is 3.85 into 10 to the power 5 kilometers. These are the points which we'll use for universal to understand the universal law of gravitation. What exactly universal of law of gravitation, its statement, its formula, everything we'll see, but these are the points which are required to understand what is exactly universal law of gravitation. The motion of moon is in circular orbit around the earth with a constant angular speed, and the symbol is omega. Angular speed we have already seen, something which is moving circular, that is angle. The speed is denoted by a symbol omega. So we'll use this symbol, and with the help of these concepts we'll find out the formula for universal law of gravitation. So let us find out. Due to circular motion of the moon, the centripetal force, we know that. What is centripetal force? Basically, centripetal, in 10th standard also we have seen, the centripetal force is basically the force which is responsible for circular motion and which holds that object to move in circular orbit. So this circular motion, and moon is obviously it is moving in a circular orbit, and it is the earth is holding it, so it is given by F is equal to mr omega square. We know this, the formula for circular motion. Fine. Centripetal force, where m is mass of the moon and r is distance between center of moon and earth. Two centers of moon and earth, and omega is angular speed. From this formula it is very clear. The Newton's second law states that F is equal to ma, that is also we know. Now if I equate equation number 1 and 2, then ma is equal to mr omega square. So here will get cancelled, and I will get a is equal to r omega square. So this is the formula which I got, a is equal to r. Further, what is omega? Omega is basically the angular velocity. Now what is the velocity? Velocity is distance upon time. So angular velocity is angular distance upon time. So omega is equal to 2 pi b. Angular distance upon time. Time is period to complete one revolution. So omega is equal to 2 pi upon t. Now if I substitute this omega, if I make square of this, and if square of this, if I substitute it here, what will happen? A is equal to r as it is, and omega, that is square. So 2 pi upon t and square of that. Right. So this is what the acceleration. This is basically acceleration on the moon due to earth. So let's see further. Substituting the values of r and t, we know what is the value of r in this. We know value of the radius 3.85. That is what I told. We will be using it into 10 to the 5 kilometer, and t also we know that is 27. So let us substitute it. So that r is 3.85 into 10 to the power 5 into, that is kilometers. So we have to substitute it into meters. So into 10 to the power 3. So we have converted it into this. 5 is kilometer, 10 to 3 is into 4 pi square. Then t is 27.3 days into 24 hours into 60 minutes into 60 seconds. That makes me meter per second square. So that if I calculate this, I will get an answer is equal to 0.0027 meter per second square. You can calculate it, you can see it. You can at this moment you can calculate it with calculator, but further, as far as the 11th and 10th standards and CETs and these calculators are not allowed, so we have to do it with log tables. On some other day, definitely we'll see how to use log table to solve such kind of problems, right? Such type of problems. So acceleration which I got is equal to 0.0027 meter per second square. So the ratio of gravitational acceleration due to earth to moon, I can calculate the ratio. Further I am calculating. What I am trying to calculate something which is the universal law of gravitation. What I am trying to find out is universal law of gravitation. For that, what I did is I have calculated acceleration on moon due to earth. So ratio of gravitational acceleration due to earth on the moon is, so any object which is there and at the surface of the earth, any object. So the gravitational acceleration on the object which is at the surface of the earth. So you just imagine this. So this is earth, and this is the orbit of moon, and this is moon, and any object is at this center. From center, this is acceleration and acceleration of this. So these are two different things, right? Acceleration on this object and acceleration on moon. So acceleration on object on the surface of the earth, we know it is 9.8. It is g. So 9.8 upon the acceleration on the moon, that is different. So that we have already calculated, that is 0.027. So the answer comes is approximately 3660. Just remember this, 3660, right? What is this? It is the ratio of acceleration on the object to the moon. Don't forget, ratio, it is ratio acceleration of object to the moon. right? So that is what is the ratio, and the answer is 3660, because we need this for further calculations. So now we will calculate the ratio of distances of the object from that ratio was for acceleration. Now we will get ratio for distances. So how will you calculate the ratio? Just see, this is what is the distance between the moon and the center of the moon and center of the earth, and this is the distance between center of the earth and center of any object. Now what is that? The ratio is, now ratio we can calculate this earth to moon distance. We know this is 3.85 kilometer into 10 to the power 5 kilometer, and 6378 is the radius of earth. Now this is the distance is actually radius of earth. So 6378 is the exact radius of kilometer. That doesn't make difference. I need not to convert it because it is a ratio of same physical quantities. So the answer comes 60. The acceleration ratio came 3600. Now this came 60. Now what is the relation between these two ratios? The area ratio is equal to square of distance ratio. 60 square is 3600, right? So the area, the acceleration ratio, the acceleration ratio is square of distance ratio, is equal to square of distance ratio. How can I conclude this? Newton's has concluded with this formula. These are all formulas are given by Newton, and Newton concluded that the acceleration on an object towards the earth is inversely proportional to the square of distance of object from the center of the earth. So this formula he is used, and that is what he wrote. Acceleration is inversely proportional to the distance between two objects. Acceleration is 1 upon r square. Now if I multiply it, another formula which we know Newton's second law is F is equal to ma. So if I substitute this, what I will get is F object gravitation. The force on object is m upon r square. So the similar force is there from earth also on the object. This is object to earth. Now what about earth to object? Earth to object, the similar force is there, and that force is F is equal to m upon r square. See, if I combine these two equations, what I get? I will get F is proportional to mm upon r square, and this is universal law of gravitation, which tells me it is proportional to mm upon r square. So the universal law of gravitation states that every particle of matter attracts every other particle of matter, half part, and second part, the force is directly proportional to product of their masses, product of their masses, that is mm, right? Product of their masses, mm, and inversely proportional to the square of distance between them upon r square. Product of masses and inversely proportional to. So I repeat universal law of gravitation statement. I repeat it. Universal gravitational law states that every particle of matter attracts every other particle of matter with a force which is directly proportional to product of their masses and inversely proportional to square of distance between them. Right. So we have seen universal law of gravitation. We have proved the formula also. We have used the ratio of acceleration and distance to prove the universal law of gravitation. Now let us move further. There is one small point which we must understand, that is gravitational constant. Now what is this gravitational constant? Because wherever you have proportionality, there is a proportionality constant always come in picture. So we know this is the formula. F is directly proportional to mm upon r square. So if I replace this proportionality constant, I have to replace with equal sign and a constant proportionality constant. This proportionality constant is called as gravitational constant. Capital G is the symbol for that. If I substitute and recalculate and find out the value of G is equal to Fr square upon mm. This formula we will be using it to solve some numericals also in future. Right, now let us find out the SI unit and the dimension of it. Now G is a gravitational constant. The value of G, you can calculate it. There are some experiments to calculate the values of G. We will see that experiment also. So G is 6.67 into 10 to the power minus 11 Newton meter square kg square. Now Newton meter square kg square is the unit of gravitational constant. So F is Newton, r square is meter square, and then kg square is right. This is Newton meter square, and this is kg square. So Newton meter square per kg square. So this is what is the unit of gravitation, SI unit of gravitational. What will be the CGS unit? CGS unit will be dyne centimeter square per gram square. Dyne centimeter square per gram square. Okay, and what is the dimension? Dimension from there also you can calculate it is L cube m minus 1 t minus 2. That is the dimension of gravitational constant, L3 m minus 1 t minus 2. Fine. So these are the points which we have seen regarding Kepler's laws and universal gravitational laws, right? So in further point we will see in the next point.